Okay, your present syllabus started in about, I think, 2022 and 2025, there is an update lah. So polarization is something new lah. It's a new topic. Okay, this is the new changes as well from the previous syllabus. Basically, looking at how to use Mallus law. Yeah, working with the transmission through a filter first, right? So working with one that is polarized already lah. So I don't have to worry about unpolarized electromagnetic wave lah. Okay, polarization. A wave is plane polarized if its vibration is in a single plane. Right? It can vibrate. The plane of vibration can be in any plane. But when it's plane polarized, it is vibrating in one single plane, as shown by the diagram there. Mechanical vibration in a single plane. In mechanical wave, example, a rope vibrating in a vertical plane, as your rope. The wave will pass through a vertical slot. It's plane polarized. The pass through is also plane polarized. Doesn't disturb at all. Pass to the slot. The slot is the polarizer, or your syllabus call it polarizing filter. The wave is said to be vertically plane polarized. Right? Vertically plane polarized. Usually, electromagnetic wave, you have a electric field and then magnetic field. So when a second polarizer called the analyzer is rotated through 90 degrees, no wave is transmitted. Okay, this is unpolarized, pass through a polarizer filter, and it's plane polarized. And it pass through another filter called analyzer. Right? If the slot is the same, or the filter axis is the same, then it will still be plane polarized, nothing changed. But if the two filter is perpendicular, then nothing comes out. If it's light, you see nothing, no, you see darkness. A Polaroid or polarizing filter is an artificial crystalline material which can be made in thin sheets. It has the property of allowing only light wave due to vibration in a particular plane to pass through. Right? Basically, just like what the slot tell you, in a particular plane, it can pass through. In another plane, it cannot pass through. It is perpendicular to the plane. It's used as a polarizer for light. Okay, instead of called polarizer, you call it polarizing filter. Okay, that is your light wave. Only transverse wave can be polarized. Light wave is a transverse wave. It can be plane polarized. Light waves such as electromagnetic wave consists of vibration of electric field. Right? Electric field is if you like, the green one, perpendicular to the magnetic field, which is vertical, is horizontal. Electric field and magnetic field, which are mutually perpendicular. Right? They are perpendicular to each other and perpendicular to the direction of motion of the wave. Unpolarized radiation, right? Usually we draw the electric field one direction, magnetic one direction. A wave in which the plane of vibration is constantly changing is called an unpolarized wave. That's what it is. Unpolarized, the plane of vibration is changing. The wave from a lamp, for example, is unpolarized, or from the sun for that matter. We can represent the intensity as a vibration in two perpendicular directions. So instead of usually we focus on electric field rather than magnetic field. So instead of drawing it polarized like that, we just represent it as two perpendicular directions. If the unpolarized wave has intensity I, each component is half I. So when it's plane polarized, we just only take one of the plane, that's all, either vertical, horizontal, or at an angle. So that becomes a plane polarized radiation. If the intensity of the unpolarized beam is I, right, that is I, the intensity of the transmitted beam through the polarizer is half I. Pass through it is half I. Is I. Pass through that is half I. When the beam is directed to another polarizer called the analyzer there, that is parallel to the wave passing through. Right? If the slot is the same, or the axis of the polarizing is the same, then it just pass through. Intensity doesn't affect it. It's called analyzer because it tells you, it allows you to tell whether the electromagnetic wave is plane polarized or unpolarized. When the axis of an analyzer is perpendicular to the polarizer, no light wave can pass through, so the observer see no light through the analyzer. So you see darkness, so if your eye is here, right? That's the purpose of the analyzer, to test whether radiation is polarized or not. Right? That one, the intensity is 0. This one, intensity is the same, half I. Polarizing filter. Polaroid is an artificial crystalline material which can be made in thin sheets. It has the property of allowing only light due to vibration in a particular plane to pass through. The other perpendicular vibration is absorbed. Okay, Mallus law, that's the important one in this topic. Mallus law. Right? I1 equals to I naught cos square theta. If the intensity of the unpolarized beam is I, and the intensity of the transmitted beam through the polarizer is I naught, is I, unpolarized, right? Passing through the polarizer becomes I naught. We are interested in only this I naught, not interested in I. If the amplitude of the light incident on the analyzer, here is the analyzer, amplitude is A, and intensity is I naught, right? I naught, amplitude A, and remember that your I naught is perpendicular to A square, or I naught equals KA square. K is a constant. I'm deriving for you, but it's not required, just for your knowledge. When the axis of analyzer is rotated through theta, the amplitude of the light transmitted is right? Amplitude becomes we are looking at there's an angle, so we are resolving it in this direction. So that's why we get amplitude is YA cos theta, right? YA cos theta. Then we put to the formula again. This becomes I1, I1, I1 K amplitude square. This is the new amplitude. A cos theta square. Then Ka square. Ka square is just I naught from here. Right? And this is called Mallus law. So your syllabus, you are not required to know how to use it, that's all. Don't need to know about derivation. Don't understand, doesn't matter. Right? And apply to polarized light only. Cannot apply to this one. Unpolarized light. Only when it's polarized. Okay, what is I in terms of I naught? What is this I in terms of I naught? Can?
Oh,
Do I not know? As one half of the intensity pass through the polarizer. That's how it looks like. Mallus law, variation of intensity with angle. Right? This is I1 K A cos theta square. At 0 degrees, I1 is I naught. At 0 degrees, intensity decreases as the angle increases and is 0 at 90 degrees. 90 degrees here, it becomes 0. After that, increase again to 180 maximum. Further increase in angle, the intensity increases to maximum of theta equals 180 degrees. Right? After that, it decreases again to 270, and then increases again to 360 maximum. Right? Or in relation to the cos graph, there's your cos graph. When you square that, that's what is happening. The positive one square, the negative one you square, it becomes positive, and then this one becomes a positive one. So if you draw right, intensity, the current, and then there is a cos square theta, then it's a straight line, equation of a straight line. This is y, there is your gradient, there's your x. Okay, and there's just an illustration to show you. Right? It's not properly drawn, very hard to draw. Okay, polarization by reflection. Right? We use it in polarized sunglasses. We don't want the glare when we go to seaside. Polarized sunglasses will cut out the reflected glare from roads because the reflected beam is partly or totally polarized.
okay.
This polarization occurs when light is reflected from any known conductor of electricity. When the polarization is total, depends on the surface and the angle of incidence. Right? This is for general knowledge. Okay, this is used by STPM student. Partly I use it because hard to find example because your syllabus is quite new. Okay, so just memorize that. Right? This formula is not given, so you need to know how to use it. Your syllabus call this one I but I call it I1 Right? We are interested in this one, not in this one. So I know is the one entering the polarizing filter, and the angle of the ionizing filter, polarizing filter, sorry, is at the angle of theta to the vertical axis. Right? This is vertically plane polarized. Then we use this formula. I1 is the transmitted intensity. Okay, what is the answer for this one? Two polarizer P1 and P2 are arranged coaxially with the polarizing axis parallel. A beam of unpolarized light of intensity I naught is directed to P1 as shown in the figure. Through what angle the polarizer P2 must be rotated about the common axis so that the intensity of the beam that emerges is 0.2 I naught. Ken, what is the answer?
Oh, which formula should I use?
Mallus formula?
Oh, okay.
Yeah, it passed through half of it. If this is your I naught here, right? There's your I naught. Examiner can play with you. He doesn't have to follow the symbol of syllabus, but we know how to use the equation. If this is I naught, then passing through will be half of it, half I naught. Then you apply Mallus law. right? This I2, this I1, then cos square theta, right? So cos theta, square root of I2 over I1. I2 is this one. I1 is that one there. I0 can cancel times 2 here. So use your calculator. Answer is donkey. Can.
Uh,
Which part not clear?
yeah, can.
Can, huh? The others you can try yourself lah. Well, let's try number 3 lah, since you already asked. Two polarizing filter. This is year 22, June paper, variant paper 1-2, question 26. Two polarizing filters are placed next to each other so that their plane are parallel. The first polarizing filter has a transmission axis of 50 degrees to the vertical, and the second polarizing filter has a transmission axis at 20 degrees to the vertical. The angle between the transmission axis of the two polarizing filter is 30. A beam of vertically polarized light of intensity 8 watt per meter square is incident normally on the first polarizing filter. And it's already polarized, so you don't have to worry. What is the intensity of the light that is transmitted from the second polarizing filter? Right? Draw a figure, roughly figure. Right? This is your I0, this is your I, there's your I1. Passing through the polarizing filter, right? Is I0. So, know what formula to use? I0, right? I0 is I cos square theta. That's your theta. Don't let this one distract you lah. This one is polarized already. Okay, it's polarized already. So use the formula. Right? This is the original intensity. This is the one that passed through the filter. That's what we are doing. This original intensity is passing through the filter, the first filter. So 8 is your I cos 50 degrees. Calculate out. And you want to find I1. Now you are told that this angle is 30 degrees to the vertical. Right? The angle between the transmission axis. We are interested in this one. Transmission axis of the two polarizing filter is 30 degrees, not the 20 degrees.
Okay.
Then the rest can do.
Yep. I haven't do yet lah because
Okay, after that,
haven't.
after the break, you can try lah. Let's
Okay.
let you give you a chance to try it out first before I go over with you. Okay, let's just watch a video so that you understand what is the standing wave.
So what we have here is a frequency generator. It's connected to what's called a wave driver speaker. It's going to pump up and down at whatever frequency I set this guy to.
This is your power generator lah. This is your vibrator. It causes a string to go up and down.
When this guy pumps up and down, well, he sends a wave. Sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, yeah, let's go a little higher. So it's sending waves back and forth, but these waves are static, if you like.
No standing wave is formed, only at a particular frequency.
They're not exhibiting consistently constructive or destructive effects at any one point. But if I set it here, for example, I have what's called a standing wave. That's the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that reflect, that come down and reflect, destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with a high-speed camera.
Remember, it's like skipping rope, except that it's going vertical.
So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because this is a node, this is a node, and the middle's a node. So we have three nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5. And there we go. It's basically the scenario of a jump. Now, I can find any of the other all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5 is around 25.5.
3 loops.
And there we go. So that's the third harmonic. How many wavelengths is this? Well, it's 1 1/2. 1 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with the high speed camera and verify for yourself that it is 1 1/2 wavelengths. So again, third harmonic, 1 1/2 wavelengths. Well, let's go to the sixth harmonic. The sixth harmonic will just be double this frequency. So we go up to 50. And there we go. That's the sixth harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through calculations and derivations.
Okay, we got 10 more minutes. So in case you got cut off, you try the question now. Okay, let's start. Okay, there's topic 8, superposition. Alright, standing wave, principle of superposition. Wave traveling in opposite direction, there's standing wave. And we go to diffraction 8.2. We will probably cover 8.1 only. There's your diffraction. Wave passing through narrow and wide gap. And interference. Right? That's basically Young's double slit interference coherent wave passing through a point, two source interference, diffraction grating, coherent wave passing through many slits, right? These two slits, these many slits, right? That's your syllabus. Right? We got time, you can watch the other video. Okay. Superposition is introduced to develop the concept of standing wave. Diffraction and interference are then studied, including two-source interference and diffraction grating. Okay, let's go to 8.1 standing waves. Don't worry about this mathematical. If you go to do physics in university, you will have to go to represent the wave as a equation, mathematical equation. When two waves of the same type, that means light and light, or sound and light, sound and sound, same speed, same wavelength or frequency, traveling in opposite direction, right? Must be one direction and the opposite direction. Cross a region, they are on passing the same region. A new waveform is produced. You don't see the individual wave anymore. You see the resultant waveform. Right? There's one standing wave to show you. Right? Usually we draw the two waves, the two wave side, to contrast it with a progressive wave. Characteristic. The wave is stationary, so we call it standing or stationary wave. The particles in the medium where the stationary waves are formed vibrates either in phase, all going up together, or all going down together, right? Especially at this part there, these are all going down together. Remain permanently stationary. This one is stationary. This part is stationary, not moving at all. Or 180 degrees out of phase. Right? If you look at a point here and a point here, they are one is going up, this one is going down, so 180 degrees out of phase. Why not is the amplitude of the two original wave. We'll look into more detail in a while. Principle of superposition. When waves meet at the same place at the same time, the resultant waveform is the sum of individual displacement. Memorize that. Right? Remember, displacement is a vector quantity. These are individual pulses. Right? When they meet, they add up. When they cross, you only see the dark one. You won't see the individual pulse. Two pulses traveling in opposite direction. Observe the resultant pulse when they meet. Okay? That's where they cross each other. That's the resultant. Okay, just a reminder, resultant displacement, one going down, one going up. Displacement is a vector quantity. If we take upward as positive, downward as negative, and this is 10 minus 4, 10 minus 6 is 4. So we can represent 10 as a vector, and then 6 going down. So answer is 4 meter going up. Right? Or if it's in the same direction, same thing, 10 meter, 6 meter, add them up together, same direction is 60 meter upwards. Right? Intensity is K amplitude square. If the amplitude is A, then the intensity is IKA square. If the amplitude is double, now it's 2A, right? Then the new intensity is K2A square, right? KA square equals to I, so it becomes 4 times I. Okay with that?
Okay.
Right? It's just a reviewing the two Remember, the two waves are on top of each other, not separate like they are here. Standing wave and interference. In standing wave and interference, let the wave of the same type, right? Light wave and light wave, sound wave and sound wave, frequency, speed, and polarization cross to produce constructive and destructive interference. Right? We are going to look at these 2 points, constructive and destructive interference. Okay, here we separate them out, but they are on top of each other. That's the resultant. Cross meet cross. Constructive interference, or some textbook will call it reinforcement. Cross of two waves are coincident, or trough of two waves are coincident. Or we say the two waves are in phase. They combine together to create an amplitude amplified wave that is known as the constructive interference. Right? This is the resultant that we see. If the amplitude, if each wave has amplitude of A and intensity I, the resultant wave has an amplitude of 2A, intensity for I. We just calculate that. For light, we observe increased intensity, while for sound, we hear a louder sound. Right? This is just to illustrate to you again, the same thing. Right? Two waves, one on top of each other. So we don't see the individual wave anymore. We see the resultant, one moving to the left, one moving to the right. Right one is the red one. The broken line one is the left one. Right? So the blue is the resultant waveform, constructive interference. If the amplitude of the wave is I and intensity is, if the amplitude of the wave, each wave is A and intensity I, what is the resultant amplitude in terms of A and I? Right? We have done that already, so we won't go into much more detail already. A plus A is 2A, resultant intensity, right? We are just repeating again. Destructive interference, when they are on top of each other, cross mid-trough, you get zero resultant amplitude. Cancellation occur when two sets of wave cross, where a wave cross meet a wave trough. Or another way of saying, the phase difference between the two waves is 180 degrees out of phase. A complete cancellation, the amplitude of both waves must be the same. So if for light, we see dark band. For sound, we see no sound. We hear no sound. Right? Amplitude must be the same. Right? It's just to illustrate to you, they are on top of each other. One moving to the left, one moving to the right. So the resultant is zero amplitude. Okay, this is illustrating the same thing again. Okay, we'll cut off anytime now.
So we're in superposition already.
We are in superposition already. After that,
Okay.
we go to standing wave.